Yes, sir.
Yes, sir.
So let us start. Now we talked about scale index byte. We talked about mod RM. So with respect to them, even like let us see few things rather in respect of other instructions that possibly may be used by an individual to really work out. Fine. Okay, so let us take this code. Now what happens is like when we use this assembly or when we use any programming language, you must have seen that like for example, if I take C language, we have integer, correct? Then we have other data types too, like char, correct? Now even we saw how an array can be used. Fine. Now when we are dealing with say something which concisely talks about float operations. For float, we don't have support through these registers, the registers that we saw. Like we saw nearly 8 registers: EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. They would not be useful. Even from perspective of instructions. Okay, what Intel did was Intel categorized it like with respect to say there would be different float instructions available, there would be different string instructions available, and so on. So first of all, in today's class, I will introduce you like how exactly the treatment is given by Intel in respect of string instructions. So we have different instruction like the way that we saw till previous session. We have never used mostly ESID, though we used it, but we used them for the perspective of separate temporary registers. So there is a specific meaning of those registers. So if you see this ESI and EDI, that I means for say an index register. For an index register. Now when we deal with such kind of aspect, ultimately, like one needs to know how exactly we would be working or we would be going in front of making use of the systems. Correct. Now let us try to understand majority of these things. Okay. Let us see. So I'm using section.data. So I'm writing now for a while a code which is not making use of any string instruction. Okay. How exactly you will calculate string length? Fine. Okay. Or let us say how exactly you will copy the string. So let us try to copy the string. So my first string, let me write source string db. This is the source string. So now you will require like how will you copy this? Suppose I have another destination string written here. Now I have to define how many bytes. So we'll try to take same number of bytes as source string is having. So there is an directive called as EQU. So how you do that? Len EQU. This is a directive $. You simply write source string. So what this does is it takes length of this is it computes length of this and it assigns here. So I'm writing here as len. So this will reserve same number of bytes as source is having. Fine. Now we have to write this code. So let us say section dot text global main colon. Now let us take strings. Move ex comma source string. Move eb edx comma destination. Now I am showing you maybe the prefixes that can be used. So if you recall, we saw a prefix for 16-bit instruction, correct, in the mod RM byte. Like we saw 66 there for 16-bit instruction. Similarly, I am going to show you a few more, or maybe how exactly they can be used. So right now I'm writing it with my simple instructions without using any string instruction. So move cx comma len. Okay, so let us try to debug this first while. So I took, I think, capital. Yeah. GCC-M32. Let us debug. Breakpoint main run. Now I'm taking this. So display $ex step. So we got this. So one can check the character by x/c $ex. So first string is your, this is the string, correct? This is my source string kind of thing, correct? Okay, let us talk about now x slash display $edx. This would not be assigned, but right now I do have 36 there. So if I try to display a character, nothing would be there. Sorry. If I try examining contents, there is nothing right now, 0. Correct. And let us display ECX. So step. So you can see. Okay, let me try running it one more time. So I got EX, I got EDX, correct, and I got ECX. ECX is 24. Fine. So if you see, if you try computing this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So that's why this 24 length is fine. Okay, so at least now we have values with us. So let us try now copying the code. So we'll do what? Move AL, sorry, move BL, comma, byte of EX, move byte of EDX, comma, BL, decrement ECX, jump not 0 to LP, and this is your LP. Here we have to increment EX and increment EDX. Both values need to be incremented addresses so that rest of the characters can be copied. Fine. And then let us write here extern to test. So push EDX. Okay, push destination string call to test add ESP comma 4. Fine. Let us see this. I will debug. I will show you output first. So we got only T, correct? So let us see the code. What exactly happened? why it is not really working with the form. So let us see the code first. So we decremented EAX. Sorry, I forgot to write this label. Nasm GCC dot slash e dot dot. Okay, good. Till let us check. EX, EDX, ECX, increment EX, increment EDX. Correct. Okay. Now let us debug. GDB dot slash a dot out. So display slash C dollar EX EDX. So I will take always EDX minus 1 because EDX would be okay. Let us check this one too. Display dollar ECX. Run. Breakpoint main run. X slash C dollar EX. So we got T. NI. Okay. Then NI. X slash C dollar EDX. So you will see T is copied. Fine. Next instruction. Display dollar EX. Display dollar EDX. So if I write X slash because EX incremented. So next value is H. We don't have because EDX is not incremented. So only T is there. Correct. Now this would be incremented. If I write this X slash C EDX, there is no character. Fine. Now decrement ECX. ECX became 23. So we are saying jump if 0 to LP. Actually, it should be jump not 0 to LP. That's why it is coming out of that code and it is printing this. You can see. Correct. So my instruction choice was wrong. So I need to write there. So here we are addressing two things. So if I write J and Z LP, then let us see the code. This is jump not 0. 0 is a flag. Now my string got copied. Correct. Now if I try to see its object code through LST file. See how many bytes are taken. So this was a code responsible for copying your or working out your what you can call it as copy operation. So number of bytes would be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we are not working upon how this is computed. We will work out. So 9 bytes are taken. So can I minimize this load of 9 bytes? Because it added this label to address computation was also happened, like how exactly it will go to LP. So we are having F7 here. Correct? How exactly this is computed. So we can understand the translation of these three instructions. Even we can understand translation of these all instructions, but it would be difficult for us to really talk about this. So probably this JNZ LP would be talking in Wednesday's class. But right now, our interest is only to really minimize this number of bytes. So how can I, instead of these many bytes, can I write a single instruction and which will take care of these 5 instructions altogether? Correct. So let us see. CP. Now what I'm doing is I'm removing this. And here I'm writing ESI source index and destination index and I'm taking ECX. Fine. And I'm only saying here USB. Fine. Now let us try to understand this. So I will explain you what exactly I did. Some first of all, let us see if it gets executed. Control C, GCC. So my code worked. Okay, let me remove this a.out even if we are not sure about. So if I write GCC and execute. So let us change the code maybe by writing different string. To be copied. So I'm adding text so that you will understand that I have generated this code again. You can see. Correct. Now if I try to check its LST, so I will take q.lst. Now see, we only took these 2 bytes. Whole stuff was done. So if I try to check even lsp.lst, try to compare. Sorry. Oh, I think I have made a change. Yeah, now compare this code. This is your LST that you had earlier, correct? Now here with these many bytes were taken. You can see here, correct? Now I did the same thing here in this code by writing simply this. Rest of the codes are same. Like if you see B, in this case it took B because my register got changed, ESI. So here it took B8 because it was EX. So it adds register number there. So EX is 0, that's why B8. And this was source string address 0, destination string address 0 from different sections. Correct. Then ECX length. So it took this 25 was computed appropriately for this length. Okay, so if you see this source was copied till that, then length was there, len. So as it was an what you can call it as directive. So after this 24, this was 00 from my source string. You can see here. For this length, nothing is shown here. Correct? Nothing is shown here. So this is my string. So till 00, it is showing me that thing. As I added now more characters, so till 67. So where is 67? Probably this one my original string. Correct? Source string, and that to be copied would be added here after this 20, 74, 6F and so on. Correct? And that's why like my address was shifted to after this was 24. So my address was shifted to 20. This length would be shifted to 25. That's how the value would be added there. Now in this case, if I see about this length, it is talking about 12, 18. Correct? So 12. So if I go on 12, 13, 14, 15, 16, 17, and it was length was 18. That's why this was taken directly here. Correct. Whenever I take any value like this, which is declared in data section, so that address would be picked. It would not be showing it as memory because this len is used through and a directive, assembly directive, and that it will help us rather to understand more things in respect of the thing. Okay, now you will see which one of this is opcode. Here I can definitely see 75 was opcode for JNZ probably. If I go there, let us check jump IJKL. Let us try seeing J. Let us apply jump instruction. So next address would be computing for J and Z would be in the next session. So yeah, so this is JCC. So let us find out where is J and Z. Yeah, you can see that J and Z 75. So the code that we got was not here, but here. It was 75. Correct? Now this F7 was computed using some method. Right now, let us not much worry about that part. Let us not much worry about that part. We will address that later. But these are the different jump instructions that could be seen, which were supported by, say, for example, the Intel instruction set. So you will see that most of the opcodes are getting repeated. Say, for example, I can see here 75. I can see here, like for example, here as well, 75. Now, how exactly it might be differentiating? If it is same, it definitely is having something internally represented there. If you see jump not carry relative weight, correct? Jump not equal, no, it's not sir, jump not equal, jump not equal 75. Jump not Z. Again, both of them are same. Jump not equal means what? It is not 0. So you can see jump short if not equal, that means ZF is 0. When you say equal, ZF would be 0. Same case, jump short if not 0, that means ZF should not be set. If it is jump if 0, if I check JZ or JE, let us check JE. JE would be this. So we will see 74 only for JZ. Jump if 0. You can check here. So both the instructions meaning the same thing. It is working on that part. So similarly, other instructions also would be working in the same pattern. Like for example, if you write this JPE or JP, jump if parity or jump if parity even, both of them would be same. Correct. So now these all jump instructions are dependent upon something called as flag register, and that flag register plays an important role in any assembly support or in AC assembly or any assembler rather. When I say or when we deal with assemblers. Now, if it is the case, what was the other stuff? Like what was this A4, F3 or A4? What this F3 means? So let me go to repeat. Okay, so let us check repeat. So let me close this. LMNO PQR. R would be the next thing. L here. LMNO PQR. Let us see R here. REP. So there are multiple versions of this repeat, this REP. You must have even identified that I am using two instructions here. One is rep, other one is move USB. So let me show you move USB first because it would be very easy for us to reach to that move S. Yeah. Move S. So when you write move SB, simply it is A4. If I see there, where is A4? A4 is here. Then what is this F3? F3 was meant for what? So let us go to that repeat prefix. Now let us search for REP. So there are multiple versions of that REP as well. The way that we saw for other instructions. Yeah. So RE repeat prefix. Yes. These are repeat string operation prefixes. So sometimes you can call them as instructions, or even you can say they are the prefixes as supported by your Intel architecture. Correct. Now if you see what was that repeat with the instruction you wrote was move SB. So do you see there SB? Like if I go back, let us see move SB. We are not seeing that, but we can see that only like S was there. So try to see whether am I getting something as R32 R32 or R32 RM32 or move S. It is saying memory. Correct. 32 memory move S. So 32-bit register. So when we use this with 32-bit register, the opcode was F3. This is F3. Now you may say we haven't used any what you can call it as memory over here. Then how exactly it referred? So actually you are using ESI and EDI internally. These ESI EDI are used here. Are used here. Now what exactly this repeat move SB is doing? Let me show you. This repeat would be working with that jump part, decrementing ECX and jump part. So let me show you the debugged version. Masm. Then let us take GCC M32-21-0301.o-g-f Let us debug this code. So let me display ESI, EDI, display ECX. Okay, let us say breakpoint main and let us run. Now try to concentrate on the execution mode, how every instruction is getting executed. So ESI got address, EDI got address. So if I try displaying value for ESI, you will see T source string, correct? So next is now see length also is there. Now ESI. Now see what exactly it is doing. Move SB. Suddenly when you execute it once, concentrate on what are the values of ESI, EDI and ECX. Are everyone got changed? Do you think all of them are changed here? What was the ESI value earlier? What was the ESI value earlier? Amol, are you there?
08.
Yeah. So if you talk about last number was 08. Now what is the ESI current value after execution of MoveSB once?
09.
So it got incremented. Am I right?
Yes, sir.
Okay. Balerao, what was about EDI? What is happening with EDI? Is that also got changed? Prasad. Okay, so now that also got changed. How about ECX? ECX also got changed. So is it taking care of same thing like copying a byte? Okay, inner temporary thing. Then again like copying from one memory to other memory location, incrementing both the addresses and then decrementing ECX. So thing was taken care of by this. So decrementing and jump was taken care of by this repeat, and move SB actually took that move string byte, move SB, move string byte, move SW, move string word, move SD, move string double. So they like the way that we see, say for example, if I go back here to move, there are multiple versions of that move S. You can see. Let's go here. Yeah. Move S B. Move S W. Move S D. Move S squad. 64-bit. Means 8 bytes. This talks about a byte. This talks about a word. This two bytes. This talks about double, 4 bytes. This talks about 8 bytes. And this is how rather it works there. Now, when we do deal with this, ultimately, what could be the logic behind MOVS P? I'm adding a change here. Okay, so like how many flag values are? So let me show you first. Let me go. Let me see if I can show you. One minute, please hold. Please hold for a while. Let me get the details of a flag register. Now it is a 32-bit register, but it only 8, or rather you can say 16 lower bits would be used by it. Okay, so let me show you that part if it is possible for. So they are different. There are different flags that could be internally used. And so let me search flag register. Yeah. 1 minute, I'm done. Yeah. See, we have 0 flag, correct? Then we have carry flag, we have overflow flag, we have sign flag, parity flag, correct? So these are mostly the what you can call it as registers which would be used for arithmetics. So these are there is auxiliary flag. Fine. So these are the flags which are meant only for status or arithmetic. Okay, in E flag register. There are 6 in E flags. Moreover, there is a control flag called direction flag. It determines whether string operation should scan the string forward or backward. It is only used in string instruction. DF can set by STD and cleared by CLD. There are system flags too. Fine. So these ones. Fine. So let me add probably this for you peoples. Okay, this was for auxiliary carry, and okay, this is about your parity flags. Sorry, these are about your flag register. What would be the different values? Now we are more interested in the DF. Okay, now you must have seen while I used in the code, if I try to check the status, so let me display E flags, parity flag, zero flag, interrupt flag, and there is RF. Fine. Now when we do deal with this particularly, these all registers, or these all you can call it as what you can call it as flags. Okay, this the RF would be a resume flag. Now if I try to run the code again, see the status of the register, status of flag register at the initial stage. How many flag values are running there, or how many flag values are set right now? Parity flag, zero flag, and interrupt flag. All of them are right now there. Fine. If I say NI, this instruction is not going to modify anything. Flag register is not changed. If I write NI, this also would not be doing anything. If I execute this, now this repeat would be making change, some arithmetic change in ECX value, as well as ESI and EDI would be getting changed. So that's why suddenly after execution of this, you will see one more flag got set. Now there would not be any change because these are set every time. So you can see the now ECX becomes 0, then it came out the code. Correct. Now you might not have seen that there was a direction flag. So let me show you what happens. Now we saw that ESI and EDI value was getting incremented. 43, 87, 44, 88, 45, 89. Can we control this execution or increment? So let me show you that part. Simply let me add here, say STD. Okay, let me come. I have added set direction flag. SM GCC. Now if I try executing, it will not show anything. It got into segmentation fault error because of the problem that I created. So what was the problem? Let us see. Display E flags, display $ESI, display $EDI, display $ACX, breakpoint main run. Now see all four values. Huh? Now when STD is there, we have PF, ZF, IF. You should see now DF. Okay. Now initial values of ESI, EDI are 852 and like ECX is 37. Now when I execute this repeat prefix when DF is there, see what happened. What happened? Can somebody tell me what happened exactly here? Anyone can tell me from you. Unmute yourself and then let me know what exactly happened here. If I execute one more time. Yeah.
Address is decremented.
Which address?
ESI and EDI.
Values in ESI and values of EDI as well as value of ECX, each one of got decremented. Anyway, ECX is going to get decremented because of this repeat. Correct? Because of this repeat. But this move SB and directional flag set caused ESI and EDI got to be decremented. That means what? If you want to decrement, then set directional flag. If you want to increment, reset directional flag. So how you do that? Let me show you. You only say here, I wrote std, let me write cld. Now let us see the change. I'm setting the direction flag, though like I could have deleted both of them, but I wanted to show you what happens here. So my code, sorry, dot slash a dot out. My code would be executed, getting executed. So let me debug. Display dollar e flags esi ed. Now we know that ECX value is anyway getting decremented because of repeat. Run esi edi ECX. Set direction flag df is there. Correct? Are you with me? Now when you execute next instruction again ni, that is removed. Clear direction flag. Now each of these flag would be having an important role. Rather, I'm not going to talk about those flags right now. The flags we are interested would be what? Jump if carry, means carry flag, zero flag, and this direction flag, if at all we have to work with. So the way that you use most of the time a flag value while writing C code, you must have seen like you use a flag, integer flag, and then you set or reset that. Actually, same thing is happening internally in the system. And all flags are altogether taken in what you can call it as this execution. Correct? In this execution. So each of the flag at particular stage would be having a value, would be having a position at that point of time. When I say at that point of time, how exactly this would be handled, if at all we are going to work with. So probably like if I have to talk more about this, what I can think of, there could be a controlled or distribution happening with respect to that 32-bit representation, which is taken care of by Intel. Okay. And Intel would be definitely addressing that part through a representation, what we are saying as a flag register. Now, if it is going to do that through the flag register, then I definitely should know what position would be there for each particular flag. So I'm sharing one image with you right now. Let us see if it is visible. Open image. One minute. This is a 32-bit representation of a flag register. Now these are the positions of that 32 bits that are there for flag register. Correct. So carry flag would be here. This position is not used. This position is not used. You can see wherever the names are. Otherwise, it would be 0 or 1. So they are taken by it, like with assumption that probably it will require some more flags to add on, which would, these positions would be given to them. So whenever you are saying jump if 0, actually it talks about this byte. What is the value here? Whether it is 0 or 1. Jump not 0, it is going to target this 7th position of that flag register from right side, from LSB side. Correct. Now, if when we said that this should be taken care of by what you can call it as your processor. we will require definitely some kind of mechanism which will check status of contents of this value 2 every time. Right? So you have to talk about that bytes. By the way, I have added that what can call it as flag registers image in the chat. I hope you must be able to see now. Can you see that? Yes. Yeah. So now if at all I have to control this, can I take an array of size 32 positions? And I will check each byte position or each character position in that array. And I'm defining a particular index of that array or a string. That would be string of zeros and ones only. So I will be going to particularly respective position of index, and then I would be either making it 0 or either I would be making it 1. And that's how I would be controlling execution of my code. Can you simulate some kind of similar kind of flag register? Think of you carry out any operation like whenever, like if I input two numbers. So my wherever my CEF is the lower significant bit. If it is 1, then I should carry multiplication. You set you do different operations depending upon what are the values there. So when I say I'm going to check, like for example, if that position say JM for example, or you give any operation like print multiplication. Now when I execute print multiplication, see if there what the value is. If it is 1, then only print multiplication. Otherwise say that your bit position is not set. Try to take this, try to simulate this flag register on your own. So like when we say flag register, we are not going to verify 2 bit positions or 2 or more bit position at a time. Only 1 bit position would be verified every time. The way that the jump instructions were shown in the what you can call it as manual, Intel manual. Let me show you that again. IJKL jump, JCC. These all J jump instructions which are conditional code, condition code. JCC means that CC meant for condition code. And that condition code would be defined depending upon flag. What is the value in the flag? Jump if condition is met, condition code, this CC. And that condition is this one. So now you will see that jump if above. So this talks about 2 bit positions. Carry flag should be 0, ZF should be 0. Then and then only it would be working. Jump if below or equal. It checks both. Jump if below or equal. Both of them should be 1. So can you simulate similar kind of stuff rather with respect to the flag register? It would be better. Like think of some operations. Fine. So I will add a description for that assignment in our Moodle site.